Hi there, my name is Dr. Tishan. In this video, we are going to use the definition of derivative to find derivatives in an analytical sense. We're going to do algebraic examples. Before we get started with that, I just want to let you know that I am filming this in my backyard. So there are some background noises that may come up that I have no control over. There might be airplanes flying overhead, dogs barking, birds chirping, nature. Nature's been a little bit noisy this morning, but it is just such a beautiful day. So I want to just do this from out here. There's plenty of space. So bear with background noises. And so here we go. Let's go ahead and use the definition of derivative. I just published a video on the definition of derivative and where it comes from, a little bit of an analytical, see where it comes from. So this is just a video of examples of how we would use it. So example number one, we want our function, we're going to do 3 total examples, right? So there's 2 on the front board and there's 1 on the back. All right. So example number 1, our function is x squared. So we're going to use the definition of derivative to find the derivative of this function. So the definition of the derivative, okay, so remember f prime of x, okay, I make my f's cursive, so this is notation means derivative. By definition, your derivative definition, it's the limit. As your delta x goes to 0, some people use h instead of a delta x, whatever you prefer. As your delta x goes to 0, it's f of x plus delta x minus f of x, and then all this is over delta x. This is your definition of derivative, okay? The previous video I just put out, it showed you where this came from. So this video we're doing examples. So let's go ahead and find the derivative of our function x squared using our definition. So the derivative of this function, it's the limit as delta x goes to 0. Now look what we have to do here, function notation. So in the numerator, we need f of x plus delta x. So you're going to take your function up here and we're going to take the x's and replace them, substitute them with x plus delta x. So x plus delta x quantity squared, okay? All right, so there is f of x plus delta x. From that, we subtract the function. What is the function? Well, the function is just x squared. I'm putting grouping symbols around here so you can see what we're doing. All this goes over delta x, okay? So you're just using function notation to rewrite the numerator. The denominator is delta x, okay? So f of x plus delta x, we replace the x's with x plus delta x, minus bring the function down here, okay? If you were to take the limit, remember to evaluate limits, you would take the 0 and just substitute it in for the delta x, whatever variable's here. When you substitute it in, it gives you 0 over 0 indeterminate form. Indeterminate form means that you're going to have to work with the expression and do something to get this, simplify the function, okay? Simplify what you have there, and we want to simplify this expression and change the form so we can evaluate it. So that's with indeterminate form. So what strategy can we use here to evaluate this? We can actually expand it. We can multiply the numerator out. We can take x plus delta x and actually square that binomial. So let's see what happens when we do that. So f prime of x, we have the limit, okay, as delta x goes to 0. When we FOIL this, you have x squared, okay, plus 2x times delta x, all right, plus your delta x, and your delta x quantity is squared, and then from that you have the minus x squared, and then all this goes over your delta x. Okay, so you want to, when you take x plus delta x and multiply by x plus delta x, right, we're squaring the binomial, you end up with a trinomial answer, and this is what it looks like. Okay, next thing we want to do, take a look in the numerator, and we want to simplify. What can we do to simplify? Well, do you see that this x squared is positive, this x squared is negative? So we can cancel these x squared. See, they cancel out because you subtracted. X squared, take away x squared, and it's gone. All right, and take a look at these 2 terms that are left over. We have this term, we have this term left over. Okay, so we have to, after we cancel the x squared, we have these 2 terms left over. Now, what do these 2 terms have in common? Do you see that we can take a delta x out of each term? Okay, so let's go ahead and write our next step simplified. So our derivative of this function, we're going to have the limit, all right, as delta x goes to 0. The numerator, the x squareds cancel, but let's go ahead and factor out a delta x from the 2 remaining terms. Take a delta x out of this term. When you take out the delta x, you have the 2x left over, okay? Plus, and you have 2 delta x's here, so you're going to factor one of them out. You're still going to have 1 left over. So there's your numerator. Denominator is delta x, all right? And can you see we can we can cancel the delta x's, okay? So we can still simplify this. So the delta x's cancel, all right? So we have the limit. All right, so here, let me write this out. So the derivative of our function is the limit, all right? Delta x is going to 0. In the numerator, the delta x's cancel, so you have 2x plus delta x. And the denominator is 1, so you just have this, okay? So now let's go ahead and take the limit. Take the limit means we're going to take the delta x and substitute the 0 in for the delta x. When you substitute 0, you're going to take the delta x and just substitute a 0 right in there for the delta x. It's going to make that delta x go away, isn't it? So what is the derivative of our function? Our final answer, the derivative of this function, when you take the 0 and plug it in, we can lose that notation. And so 2x is the derivative of our function here, okay? So the derivative expression is of our function is 2x, okay? So, I mean, the graph of the function is a parabola. It is a parabola. If you draw a tangent line at any point to the parabola and you want the slope of that tangent line, okay? So, you know, parabola looks like, so the tangent line, well, you know, you might be slant, you know, depending on the point you pick on the parabola, your slope is going to be different at every point. If you want the point at any of those tangent lines on the parabola, you take the x coordinate and double it, and it'll tell you what the slope is. Okay, so this is what the derivative tells us. It gives you a rate of change at an instant on the function. So that's what it does. And here's algebraically how you would go through and work it out. Okay, let's do another example that happens to be a quadratic, a little bit more difficult than this, and then we have a rational example on the back board. So let's take a look at example number 2. What do we want to do here? We want to use the definition of derivative to compute the derivative, to find the derivative. So how do we find the derivative? To find the derivative, we take the limit. As delta x goes to 0, f of x plus delta x minus f of x, all that goes over delta x. That is your definition of derivative. There's the definition of derivative. We want to write the definition in terms of our function given to us, the 1 minus 3x squared. So we want to compute the derivative. It's the limit. As delta x goes to 0, and here we go. Let's go ahead and put our function notation in there. We want f of x plus delta x. So you go to your function, and we're going to replace the x's, make a substitution, replace the x's with x plus delta x. So you have 1 minus 3 times the quantity, and you're going to replace the x with x plus delta x. We're going to square that, okay? And then from that, we subtract the function, which is 1 minus 3x squared. Note the grouping symbols. Note the grouping symbols because this is subtracting the function. If your function has more than one term, you have to subtract each term of the function. And then your denominator is delta x. Okay? So function notation, you're just replacing each expression using function notation. All right? Now what? Well, if you actually did try to take 0, substitute it in for delta x, and compute the limit, you would get indeterminate form. You always get indeterminate form with your definition of derivative. So we have to algebraically change the form of this expression here, and we will do this by expanding is the technique we'll use here as well. So we have f prime of x. It's the limit. Delta x goes to 0. Okay, so delta x goes to 0. Here we have 1 minus 3 times, let me go ahead and square and then I'll distribute the 3. When you square this expression, you're going to have x squared, okay, plus 2 times x and delta x, and then you get delta x quantity squared, okay? So we have this when we distribute, and then we want to distribute this negative sign, so we're going to distribute, so minus 1, and then be careful here because when you distribute the negative sign, minus a negative 3x squared, so positive 3x squared. There's your numerator, and all this goes over delta x, okay? So we want to expand, and I'm just order of operations. So when you do the expand, you're going to have to apply the exponent before we distribute the negative 3 out front. Doing this in separate steps so you see all the pieces, okay? So we went ahead and we took x plus delta x times x plus delta x. We FOILed that out, distributive property, we multiply that out. Now let me just, another step, I'm going to distribute the negative 3 so I can have all my terms listed here, but I'm going to now, in this separate step, I'm going to distribute the negative 3 so you can see all the algebra maneuvers here. So our derivative is, it's the limit. Delta x goes to 0. Numerator, we have 1 minus 3x squared. Distribute the negative 3 minus 6x delta x. Distribute the negative 3, so minus 3 times delta x quantity squared. Out here, minus 1 and plus 3x squared. And all this goes over our denominator, which is delta x. Okay? Simplify. Let's see. What do we have here? Can you see that this is a positive 1? This over here is a negative 1. Okay, so 1 minus 1, so they cancel, don't they? Okay, you see anything else? We have a negative 3x squared here, and we have a positive 3x squared here. Negative 3x squared and positive 3x, and they cancel. Okay, do you see they cancel also? All right, what's left over in the numerator? We have these two terms left in the numerator. Can you see if I underline them here in red? We have those two terms left over in the numerator. What I'm going to do with those two terms is I'm going to factor out the delta x, okay? Just the delta x. Yes, I see the negative 3 factors out also. I'm going to leave that alone. I'm going to take the delta x out because I'm seeing that I want to cancel that delta x with my denominator. So what do I have for the derivative of my function? Well, it's the limit. Haven't taken the limit yet, so I'm still writing the limit as delta x goes to 0. In the numerator, these two terms I underlined in red, I'm going to take out a delta x, okay? Take out a delta x in this term, negative 6x is what I have, okay? And then take out a delta x in this term, and I have the minus 3, and I still have a delta x left over. My denominator, I still have that delta x in the denominator, okay? So I still have the delta x in the denominator. Now, I can cancel my delta x's. Numerator and denominator, I can make these delta x's go away, okay? So I can cancel those out, all right? However you decided to simplify, it's going to come out to the same thing, isn't it? Okay? So after we cancel the delta x's, where are we? F prime of x, we've got the limit, right? Delta x goes to 0. What's left over? Well, the denominator's gone, so it's 1. So these cancel out, so all we really have is negative 6x minus 3 delta x. That's what we have left over. Let's go ahead now and take the limit here. Remember, taking the limit, you're going to take this number here and substitute it in for this variable. We put 0 in for delta x. Substitution. So put the 0 in for the delta x term. It makes that whole term go away. So what do we have for a derivative here? After we take the limit, the derivative of this function, now we took the limit, so we're not going to write that expression anymore. After we take the limit, negative 6x, there is the derivative for the function of 1 minus 3x squared. So the derivative is negative 6 times x. Here's the derivative of this function, okay? So this is how you would algebraically, step by step, apply the definition of derivative to a quadratic function. All right, now let's take a look at a rational function. I've got that on the backboard, so we'll take a look at a rational function next, okay? So one more example, and it's a little bit more involved. So let's take a look at a rational function, and it's over here on the backboard. So let's flip this board around, and let's look at this example. All right, last example, number 3. Function here is 2x over x plus 1. 2x over x plus 1, and what do we want to do here? We're going to use the definition of derivative to find the derivative, all right? And what is that definition of derivative? The definition of derivative, it's the limit as delta x goes to 0, f of x plus delta x minus the function all over delta x. Definition of derivative, okay? This is the definition. This is going to give us the rate of change of this function. All right, so let's go ahead and be careful here, right, with the rational expression. Be careful, but let's go ahead, substitute in with the function notation, okay? So let's go ahead and substitute our function into this, okay? So we end up with a limit as delta x goes to 0. In the numerator, f of x plus delta x, I have to go to my function and change the x's to x plus delta x. That gives me in the numerator 2 quantity x plus delta x over, and that gives me x plus delta x, I'm substituted in, and then plus 1, okay? So here is my first term. f of x plus delta x. So I'm going to take my function here and I'm going to substitute in for x. I'm going to substitute in the x plus delta x in for the x, okay? Minus, now I'm going to subtract the function. Just bring the function down 2x over x plus 1. Substitute the function, and all this goes over delta x. We're here, okay? So how does this look? So we're here. So now if you take the 0 substituted in for delta x, you will get 0 over 0 indeterminate form. So what do we have to do here? We're going to have to take this and change its form. We have to do something to simplify this. And this is a complex fraction, so we are going to simplify complex fraction. That's the strategy we're going to use here. So to simplify this complex fraction, we're going to multiply numerator and denominator by this expression. So x plus delta x plus 1 times x plus 1, and then over, whatever you do with the numerator, same thing with the denominator, x plus delta x plus 1 times the quantity x plus 1, okay? So we're going to simplify the complex fraction. That's what we have to use here. That's the strategy for this. So let's go ahead and do the algebra here. So to find the derivative of our function, we take the limit as delta x goes to 0. All right, and we want to distribute here. We want to take this in the numerator. We're going to distribute in the numerator. We're going to distribute this expression to each term. When you distribute this expression to the first fraction, your trinomials will cancel, and you'll have 2 times your x plus delta x. Okay, now the trinomials cancel, but the binomial doesn't, so times x plus 1, okay? All right, so when you distribute this here to the first term, your trinomials cancel. The trinomials cancel, but you still have this left over, okay? Now we're going to distribute to this term. When you distribute to this term, the binomials cancel, so you have the 2x, but the trinomials do not, x plus delta x plus 1. And then in your denominator, you have the delta x already there, and then you have to multiply by trinomial and binomial. Okay, so this is what we have. So complex fractions are gone. Complex fractions simplified in one step. So you want to take this expression, distribute it to each term in the numerator. Distribute, the trinomials go away, but you have the numerator and the binomial left over. Distribute it to this term here, the binomials go away, so you've got the numerator and the trinomial left over. Denominator, leave it in factored form. Leave it in factored form because we'll cancel common terms shortly. All right? Next thing we want to do is we want to go ahead, we have to expand the numerator, right? So we have to expand the numerator, so let's multiply everything out here. I'm going to multiply binomial times 2, all in one step. So f prime of x is equal to the limit delta x goes to 0. When you expand the numerator, x squared times 2, so you have 2x squared, okay? And then the outside terms is going to give you x times 2, okay, so plus 2x. The inside term, you have x plus delta x times 2, okay, so you have 2 times x times delta x, okay? And then your last term, you have a delta x, and it's times 2. So 2 delta x, we have this, okay? And then here we want to distribute the negative 2x to each term, so minus 2x squared, and then distribute to this term here, so you have minus 2x delta x, and then distribute one more time to the positive 1, so you have a minus 2x, okay? So here's this. So we had to actually multiply out this term here, okay? And then notice we had to distribute the negative 2x to each of those 3 terms, okay? Now there's your numerator. All this goes over our denominator, which what do we have? We have delta x, okay? We have trinomial x plus delta x plus 1, and we have x plus 1, all right? So we're here. Now what? Now let's go ahead, look in the numerator and see if we have common terms to cancel. Let's see about simplifying this, okay? What do we have? We have 2x squared, all right, and a negative 2x squared. Okay, so there's 2x squared, take away 2x squared, they're gone. So anything else? Okay, we have a positive 2x and we have a negative 2x. Okay, so 2x take away 2x's, they're gone. All right, anything else? Actually, yes, we have a positive 2x delta x expression and we have a negative 2x delta x. You see that? They cancel. Okay, so that all cancels out. All right, so what do we have left over in the numerator? I'm going to try to write way down here. So what do we have left over in the numerator, right? So remember, we're taking the limit. Delta x goes to 0. We haven't done that yet, so we need to keep writing that down. Numerator, everything canceled out except for this one term, 2 delta x, okay? Everything else canceled out except for 2 delta x, right? What about our denominator? Well, our denominator, leave it in factored form. So what do we have here? We have delta x. We have trinomial x plus delta x plus 1. We have binomial x plus 1. All right? So take a look what we have way down here on the screen. Is there anything else we can possibly do to simplify this algebraic fraction? Yes, we can cancel the delta x's. And you need to do that because we need to get the 0 over 0 out of there, okay? Cancel the delta x's, okay? So now what do we have? Well, okay, I'm going to travel. All right, I'm running out of space here, so follow the arrows. I'm going to travel over to here. All right, so what do we have left over when we simplify this? We have the derivative f prime of x. It's the limit as delta x goes to 0. All right, in the numerator, we have a 2. Okay, so the numerator's 2. What do we have in the denominator? In the denominator, the delta x's cancel, so we have that trinomial times that binomial. Okay, so we have that trinomial, which is x plus delta x plus 1 times the binomial, which is x plus 1. Okay, so you see here, so we cancel the delta x's and we have this expression over there. All right, now let's take the limit. All right, let's take the limit. So take the limit means you're going to take the 0 and we're just going to substitute it in for delta x, okay? So take this, just substitute it in. You substitute it in because that's what we do when we take limits, right? It's a direct substitution principle. So f prime of x, all right? So I substituted in the 0 for the delta x. So since I took the limit, I don't have to write that expression down. I have 2 in the numerator. And I substitute the 0 in, gives me an x plus 1 here, and then I still have that x plus 1 here. So this is my answer. Because I do have a common factor represented twice in the denominator, I can also write my answer as 2 over, and then in the denominator, x plus 1 quantity squared. So here is the derivative. Here's the derivative that we're looking for. All right, so given the function 2x over x plus 1, we had to compute the derivative, its rate of change equation. The derivative of that function is 2 over x plus 1 quantity squared, okay? So here's 3 pretty involved examples of how to use the definition of derivative in an algebraic sense with some quadratic functions and with a rational function. Thank you for dealing with background noises. An airplane just flew overhead, kids playing, dogs barking, birds chirping, but you know, it's beautiful out here, so thank you for putting up with that. Hopefully the background noise wasn't too bad. I appreciate you watching. Thank you so much, and that's it. Bye-bye.